Hello everyone, and welcome to the beginning of the fantastic chapter where we're gonna finally teach you how should we use all those derivatives we learned how to find. We taught you how to find the first derivative, second derivative, fifth derivative, sine, cosine, logarithms, and so on. But why are we doing all of this? What are applications of all of these things? And one of the most fascinating applications is finding maximum and minimum of functions and some kind of behaviors and so on. This might be part of your future career, and hopefully you will enjoy this video and you will see how fascinating mathematics is when it's being applied to real life world application. So I found a graph from the internet of the coronavirus spread and several cases. What's gonna happen if we are going to have no intervention when we know that there is an outbreak, pandemic outbreak in the world, then the amount of sick people hits this high level and then goes down. Or when we have some kind of intervention, which is going to reduce number of overall cases and health effects. That's with intervention. For example, we told people, please stay at home, wash your hands, don't go to the cinema anymore, don't attend that fantastic festival you really wanted to attend, and so on. Also, if you feel sick, please don't go to work, which is most of us usually do, unfortunately, because we don't want to get fired, or we just want for work to be done. So this is a real-life graph, and it's a very nice example to show how derivative will help us to identify what is the highest number of sick people can happen and what is the lowest number of sick people can happen. So what do you see here? I see with no intervention, the graph is growing fast, and actually we call it exponential growth, and that's why we taught you exponential logarithmic functions. Hit this highest point over here. You see, it's like if I'm climbing this mountain up, then it's the tip of the mountain. I see everything from that tip. And then after that, it starts decaying. Do you know why it starts decaying? At some point, there will be no people to make sick anymore. So most of the epidemics have to go down, and it usually hits the maximum and then goes down because there is no one else to make sick if everyone is already sick or dead. Optimistic point of view. But it's going down after this and settles down. So what this peak is, how to call it? It's exactly what we call absolute maximum. And then if you imagine the reversed type of graph, when something goes down and looks like a pit and then goes up, then the bottom of this pit will be called absolute minimum. So that's what we're going to call absolute maximum and absolute minimum. But let's define it somehow and then connect it with finding derivatives. So let's define it using mathematics. And I can say that, how do you know intuitionally that this was absolute maximum? Well, because this is the highest point on the graph, right? But mathematically speaking, I want to say that at this moment in time, because this is days, numbers of days, since the first case started, this is the point in time, let's call it C. And then what's happened with f of C? So f of C seems to be bigger than any other f of A, right? It's bigger than this point, which is f of, I don't know, C minus 5, or this one, which is f C plus 7. And that's how we know that absolute maximum. That's exactly what definition will tell us. Definition of the absolute maximum is if f is defined on a set D that has C, it contains C, then if f of C, and I'll put it in the box, f of C is greater or equal than any other f of x for every x in D, every x in D. So we checked all of the other inputs and f of C is still greater or equal. Why there's an equal sign over here? Because it is possible to have a second exactly the same height peak, right? And then we have two absolute maximums and they have the same output, the same height. That's why we want to make sure that we don't forget that. Then f of C is called absolute maximum. Also it's called absolute extreme value or absolute global value. On value of f on the domain D we're talking about. How about minimum? Minimum have the same idea. How do I know that this point is the bottom of the pit? Because at some C, f of C seems to be smaller than any other f, right? So this is how we're going to define with different color. If f of C is less or equal than f of x for any other x in D, so we checked all other inputs, and the outputs of all of those inputs are still bigger than what I have right now, then this is what we call absolute minimum or absolute extreme value or global minimum. And absolute extreme value is either absolute maximum or absolute minimum. That's why my title says absolute maximum minimum or global extrema. You can see that in books sometimes. Global extrema, global extreme value, global maximum, global minimum. Okay, a question for you. Does a function always have absolute extreme value or not? Well, from this graph, it seems like it always has absolute maximum. The first graph, look at that. Both cases have absolute maximum. And we say, yeah, it has absolute maximum. I can see the top of the mountain, but actually might not have absolute minimum, right? So the answer is no, it's not always the case. And here are nice examples. And we're going to be talking about absolute maximum. Here with minimum is the same thing. Let's look closely on those examples. For the first case, we're talking about parabola. This is a parabola y equals 4 minus x squared. And here I know, and we even know how to find it. This is the vertex. We have a formula for the vertex. Absolute maximum happens at 4 because basically there's a shift going on. It's shifted by 4 units up. So there's an absolute maximum at 4. The maximum is 4 at x equals 0. So this point is 0,4. But do you see any absolute minimum? I don't see it because it's keep decreasing forever and left and right. There is no minimum value and there is no absolute minimum value. Okay, so now we know example that sometimes it can be the biggest number, but there is no smallest number. Then there's example when we're working on the same function, 4 minus x squared, but on a closed interval, 0, including 0, and 2, including 2. Then we have both absolute maximum happens at 0, and it is 4. Absolute minimum happens at 2, and it is 0, right? That's minimum value, the smallest height. Imagine I'm hiking this mountain, now I'm going down. So the tip of this mountain was 4, height was 4, and I was going down and reached the bottom, which is basically the ground, and now the height is 0. That's minimum. Now, here's the case when we have no absolute maximum because I did not include 0 on the interval. You see this thing? 0 is not included. Then I cannot claim that 4 is absolute maximum because it's not defined. Go back to the definition, you will see f supposed to be only looked at its own domain. So this is my domain. Domain is where my inputs are allowed. 0 is not allowed as an input, so f of 0 doesn't exist here. But 2 is still allowed, so there is absolute minimum and it's still 0. And finally, if I don't include both ends, then there is a case when there is no absolute minimum, no absolute maximum. Even though the function is obviously decreasing over here, we still cannot claim that there is any absolute extreme value at all. So this is a nice example. So the answer to that question was no. Then mathematicians asked, okay, then can I know which functions have extreme values? Because we were gonna give you tests to identify those extreme values, and I don't want to waste time on the function which doesn't even have any. What if I don't have a graph? Can I just have a very nice straightforward way to say, this is the function I will be working on because this function has some kind of extreme value? Yes, there's the extreme value theorem, which says if a function is continuous, so it should be continuous, which means it's not fair to look at the function that has a break like this, that's not what we want to. And even if we have this function, maybe we're just gonna only look at it in some intervals and then identify maximum, minimum there. So we're gonna break it in pieces. So the function should be continuous on the closed interval. Why this is important? I want to avoid this is situations we had in C and D. So this case, when there's no minimum and no absolute maximum, in this case, no absolute maximum or minimum, and so on. I want to avoid the situations when we don't include ends. Then, if function is continuous, there is no jump, the interval is closed, then we definitely can say that it has absolute maximum and absolute minimum on that particular interval. So it's going to be case A and B. You see, the parabola is there. It's either on negative infinity to infinity, then it definitely has absolute maximum or minimum. If it's on the closed interval, it still definitely has absolute maximum or minimum, or both, because it did not jump and ends are included. Not too bad. Now, are there any other things we want to consider? What if we have several tips of the mountains and several pits as well? How can we describe that? So here's a nice idea of the second case. If right now we're having this pandemic of coronavirus, COVID-19, so I will even gonna sign it for you guys, COVID-19. Who knows, if you're watching this video in like 10 years later, then you will be reviewing this news from 2019. So if we told people to stay at home and wash their hands and please don't go out if you feel sick and so on, this is the graph of the pandemic outbreak. It reduces number of overall cases, have better health effects, reduces the peak number of cases and related demands on the hospitals and infrastructure. So basically, as people go to hospitals are not overwhelmed anymore, and that is good. Less people are dying. So my question is, what if all of us were sitting at home and then people got bored and just not responsible? And then there's some very fancy concert was not cancelled. And then people said, you know what? I'm sitting at home for like 3 weeks already. I'm super tired. This concert of my favorite group is going to be performing. I'm going to go to that concert. And then the whole city decided to do that. And then they all met at the concert and number of cases jumped up because of the concert. Say just an example. Please don't do that. Be responsible citizen, okay? But for example, it happened. Then look what happened. We have one tip of the mountain here, one tip of the mountain here. Also, we had a pit here, and say one more pit over here. How can we compare these? And are they all the same? Are they different? How can we identify them? And also, how can we just define vocally what is that? So this tip now, if I'm including both of these, is not the biggest anymore, right? So, which means I cannot call it global, because global means the biggest one. And we just define it that f of this value should be the biggest number. Now it's not anymore. Then we're going to call it local. It's going to be local maximum, because this value is still important for the data and analysis. And the definition of this local maximum and local minimum follows from the idea that it's still the biggest value, but only over here, in some kind of interval, It's not everywhere. It's not the biggest value everywhere, but it's the biggest output close enough, in some kind of interval. Same here. This value is the smallest one, maybe not everywhere. Maybe it is everywhere, but at least we definitely can say it is the minimum here in the interval. So this is a nice definition of local minimum and maximum, or local extrema, local extreme values. Local maximum and minimum values are defined as follows. Say C again is defined in our interior point of some interval I, and this interval, and F is defined in that interval. then if f of c is greater or equal than f of x, but not everywhere, for all x on that interval. You see, on interval I. And that's what I'm calling here interval I. How big or small this interval is depends on the situation, but usually it's not very big. Then we call this f of c a local maximum. And the same idea, if it's f of c is less or equal than all other f of x for all x on the interval now. So this is my interval I interval, that's why we're using I letter. Then we call this f of c local minimum. Makes sense? So it's basically a local pit or a local tip of the mountain. That's the idea. Now, where should we look for those values? That's a good question. What should we check? Now the derivative comes in, and I will ask you this question. Do you remember we were teaching you that if I'm climbing this mountain up, going up, going up, going up, what happens with derivative there? The derivative is, yes, it's positive. It's positive over here and over here and over here. But then it becomes positive in a less sense, which means there's a difference between being positive like plus 100 or over here plus 5. So in absolute value, it becomes still positive but smaller. And then at some point, what is happening over here? Remember, f prime is 0 here. Then the derivatives goes down. So I'm climbing down, hiking down this mountain. So derivative is negative, 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 and so on. Make sense? So this will help us to identify maximums and minimums. Same with the minimum. First derivative was negative, right? Then derivative became 0. Then going up, derivative is positive. Nice. So now we have some kind of intuition of this. This is very important. The derivative is 0 when I'm looking at maximum or minimum, the tip of the mountain or the pit of the hole. So, the bottom of the pit. Yes, that's what I want to say. So where should we look when we're looking for local or global maximum or minimum? Check the derivative. Check the derivative. And you're supposed to see something important from the derivative. And that's where the local extreme value theorem comes in. It also has a name, Fermat theorem. Fermat was a brilliant mathematician. Fermat with silent T. Fermat's theorem. Fermat said, you know what? If f has a local maximum or minimum value at c, and f prime exists there, then the derivative is 0. That's exactly what we just together analyzed from the graph of the function, a realistic function that actually represents the spread of the virus. And we realized, so we see that at the maximum minimum, the derivative is 0 if derivative exists there at all. However, this is a good example of a necessary but not sufficient condition, because the maximum and minimum might appear when derivative does not exist. Is it bad if derivative doesn't exist? What happens with the graph when derivative doesn't exist? Does it mean that there is no function there? It's not continuous? Not always. So yes, derivative doesn't exist when the function is discontinuous. We remember that. There's no derivatives over here, the jump, for example, and so on. No derivative. But there was a situation when the function is still continuous, but doesn't have derivative. Do you remember the example? Cusps or sharp corners. Local extrema can occur at points where derivative does not exist. For example, I found you the graph of the function. Do you remember what this function is? Does it look familiar to you? It's absolute value of x. Good job if you said it out loud. So there is no derivative, so I will call it f. F of x is absolute value of x. The derivative at 0 does not exist, d and e. Over here, go back and review the material of the derivative and necessary condition for derivative to exist. to understand why. But basically the explanation is when we zoom in a lot, when we zoom in, it doesn't become a flat line. So the slope is negative, 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 and then it's too fast becomes positive. So what is happening at this little point, you know? It's over here or like over this or over this. Since it's not obvious and we cannot claim what kind of slope happens at the bottom, there is no slope at all, so we say there's no derivative. That's a vague explanation of the situation. I encourage you to go back and check why absolute value is a good example of when a derivative doesn't exist at some point, in this case 0, even though it is continuous. So, with the definition we just gave you, well, not the definition, the theorem, Fermat's theorem, tells you, look, where derivative is 0, but it's not sufficient. It's not sufficient. There are more cases when derivative f prime d and e over here, f prime of 0, d and e, but they're still global, but f at 0 has global minimum. So we need the way to include those cases, right? So this is my global minimum. Global minimum. Global extreme value is over there. Ugly O, fixed. Well, then we need to define the new type of points, which will include both, where derivative is 0 and derivative doesn't exist. And that's exactly what we call critical points. Definition of critical point says that if we have an integral point C on the domain of the function f, and two things happen, either the derivative there is 0 at C, or the derivative doesn't exist at C, right? I'll write down D and E doesn't exist. Then we're going to call it a critical point of f. A critical point of f. That's a definition, a very important definition. I'll put it in the red box for you to show you that this is going to be very important. We will be asking this a lot in many exams because you have to know this. It's just really important for science. That's what we call critical point. In the literature, you also will find critical value. So point is something that has A and B, right? This is the pair of two numbers, A, B. That's the point. If you ask, so that's what we call critical point. If they ask you to find critical value, then it's only x equals A, or input equals A. That's critical value. Also, there is critical number notation, critical number. That's the same thing, x equals A. So only input, basically. That's input. Input only. Whatever it is, x equals A, t equals A, and so on. Okay. Now, one more exception. Oh my gosh, one more exception. Exception tells me that sometimes the cases where derivative is 0 or doesn't exist, but it's not maximum or minimum. So I cannot claim that critical point always gives me maximum or minimum. That means I need to write down an important phrase, note. I would say this was note 1, but it's just an annotation. Note 2 is actually very important. Note 2 tells me that we call these critical points, PS, are candidates. That's it. That's the important point. So when I found all the critical points, I can say this phrase: if they are maximum and minimums in this function, then they are only at critical points. There's no other places to check because maximum and minimum occur when the derivative of the function is 0 or d and e. That's it. So look again at the graph to make sure you understand that. Here's the graph of the pandemic. If they are tips of the mountain or bottom of the pits, they only occur when derivatives are 0 or d and e. So the d and e case will be like over here, will be sharp corner, for example, but it's still absolute, some kind of maximum there, absolute or local. But maybe it's not maximum and minimum even though the derivative is 0 or D and E. That's why we call them candidates. They're candidates. And you should use tests. You should use tests. Use tests to identify or check or basically test those candidates if they actually give you absolute or local extreme values. Those tests we're going to go to different video. Say first derivative test, second derivative test, and so on. Why this is the case? Because here are examples. Sometimes the derivative might be 0, but there is no local or global maximum minimum. Look at this. The function was growing, the graph of the function is increasing. So the derivative is positive, right? Then the derivative is 0, but it did not become negative after that. It's keep growing. So this is not maximum and minimum. I don't see that this is the tip of the mountain or the bottom of the pit, right? So this is one of the examples. This is example of the vertical graph of the function. And you know, if there's a vertical slope, derivative doesn't exist there as well. So f prime, here the D in E, because so the derivative was negative, decreasing, stopped or basically became completely vertical. It's not increasing and not decreasing anymore. Decreasing. So it's not derivative decreasing. The function is decreasing, derivative is negative. It was negative before and still negative after that. So at this point, it's not the graph of the function, it has no maximum or minimum. The derivative just doesn't exist there. Same here. So in this case, the slope is flat, derivative is 0. In this case, the slope is vertical, derivative D and E, but no absolute extreme values. And this goes to the different videos. We're going to teach you how to test if your candidate, you found those candidates, give you extreme values. For now, let's just have an example. Finding the critical points. And that's going to be the last part of the video. Let's find critical points. Okay, to find critical points, now I know what to do. I will be finding derivative. Find f prime of x. From now on, critical points will be a synonym of you finding derivative. That's what I will be teaching and mentioning from time to time. F prime of this function is, I will have to use quotient rule, right? U over v. Derivative of this function is square the denominator. I always start with this part, not to forget at the end. Differentiate the top, that's 1, copy the bottom, x squared plus 1, minus, copy the top, differentiate the bottom. Hopefully you already know how to do it fast. Now simplify a little bit. Don't do anything with the denominator. Don't touch the square of the sum or difference, it's good like that. At the top though, we're going to have x squared plus 1 minus 2x squared, which becomes x squared plus 1 in the denominator squared, and then x squared minus 2x squared becomes minus x squared. And what we needed to do, we needed to find, so this is my f prime, I found it, good job. We found f prime, that's why we were practicing doing it for months, that we need you to be able to find derivative of any kind of function. So now I want you to find where the top is 0 and the bottom is 0. The top of the fraction, when it's 0, that gives you critical values where derivative is 0, right? The bottom 0 gives you the points where the whole derivative is d and e. So now make a note. F prime is 0 when the numerator of the fraction is 0. F prime is d and e when the denominator is 0. Make sense? Now let's do it. So 1 minus x squared is 0. X squared is 1. Solution of that equation is, what are you saying? No, you forgot negative 1. Plus or minus 1. Did you forget negative 1? I'm pretty sure many of you did. So there are two solutions, plus 1 and negative 1. Don't forget that. Now, what about denominator? So I will do 1 and 2. Denominator, x squared plus 1 squared equals 0. two ways to see it. Either you right away can tell me that there's no solution here because, excuse me, I'm having x squared, which is always positive or 0. Then I'm adding 1, which is positive. And then I'm squaring the whole thing. That thing will never be 0. Or I can keep going and tell you that, do you see it now? X squared plus 1 cannot be 0. Or x squared cannot be negative. Then if you get to this case, you just say that there's no solutions here. No solutions, which is fine. That means this derivative is never d and e, right? So we have 2 points, we have 2 values. Those, what we just found, that's going to be important for your homework and understanding in general. Those are critical values because x is the value, right? Critical values are x equals plus minus 1. Now, what I want you to find are points. So I will move this graph a little bit lower. And I want to find points because that's what we ask you to find. Let's check. The problem tells me, find critical points. Points are pairs. So I need to find points. I can even make steps. Step 1, find a derivative. I finished that. Then step 2, plug critical values into original function f of x. Then I will get critical points. When x is 1, do you remember the function? The function is x over x squared plus 1. Then f of 1 will be, okay, if you don't remember, let's write it down. F of x is x over x squared plus 1. F of 1 will be 1 over 1 plus 1, which is 2, 1/2. When x is negative 1, f of negative 1 is 1 over, but negative 1 this time. And then still x squared plus 1 gives you 2, because negative 1 squared is 2. So that's negative 1/2. So we have 2 points now. We have 2 critical points. 2 critical points. Let's finally finish. Critical points, CPs, are 1 and 1/2, comma, negative 1 and negative 1/2. Those are critical points, and this is the answer for this problem. Now, we never ask you to find absolute minimum or local minimum or absolute maximum or local maximum. This has nothing to do to this right now because we still need to learn how to test these points if they give you any global or local extreme values. But one of the tests is to look at the graph. And here's the graph. I found the graph of this function for you. And indeed, we're going to teach you which tests are the best to use for these cases. But indeed, when I look here at negative 1 and negative 1/2, that's the second couple I'm working with, local minimum, look at that. When I'm looking at the pair 1, 1/2, that's the first pair, it is local maximum over there. You see? Local or global, we have to figure this out later using the different tests as well. So we need much more to learn now, but this was a beautiful introduction to an amazing topic. You'll be so shocked. I will explain you why the size of your smartphone screen in your pocket has that kind of size. Because it was calculating using local and global extreme values. Why the window in your room has this shape. Look in your room. What kind of window do you see? Why it's not bigger or smaller? Because it was calculated mathematically using derivatives and the local or global extreme values were found. Why this red light stop has this type of interval you see when you drive, and also it's different at night and at daytime. Mathematicians calculated that using derivatives. So this is an amazing chapter, and I promise you, you will fall in love with these topics. Maybe we'll switch to math major if you're not there yet, or we'll become mathematicians for the rest of your life after finding out all those beautiful applications. Stay motivated, work hard, and you will do great. Thank you for watching.